In the vast expanses of the universe, neutron stars are remnants of massive stars that have succumbed to gravitational collapse. When two neutron stars, incredibly dense remnants of once luminous giants, collide, an unimaginable event unfolds, a cosmic symphony marked by the violent merging of these stellar titans. The collision creates an intense gravitational wave that ripples through the fabric of space-time, detectable by advanced observatories and signaling an astronomical event like no other. As the neutron stars draw closer, their gravitational pull begins to distort and deform them, leading to a dramatic increase in temperature and pressure. This extreme environment allows for nuclear interactions that produce exotic matter, including heavy elements like gold and platinum. The collision not only generates an astonishing amount of energy, but also catalyzes the formation of these precious metals, scattering them across the cosmos like celestial confetti, enriching the universe with heavy elements that contribute to the formation of new stars and planets. In the aftermath of the collision, a powerful gamma-ray burst is emitted, a flash of high-energy radiation observable across vast distances. This burst, lasting only seconds but extraordinarily intense, originates from the accretion of material around a newly formed black hole or a rapidly rotating neutron star, known as a kilonova. It signifies the death throes of the neutron stars, undergoing a transformation that reshapes their very existence in a captivating display of cosmic power and beauty. The gravitational waves produced by such an event can be detected long after the collision, providing astronomers with a heartbeat of the universe. Alongside gravitational observations, electromagnetic signals, including visible light and X-rays, reveal the aftermath of the merger, allowing scientists to piece together the cosmic puzzle. This interplay between gravitational waves and light has ushered in a new era of multi-messenger astronomy, enabling researchers to study cosmic phenomena in unprecedented detail, unlocking secrets of the universe's origins. Moreover, the implications of neutron star collisions extend beyond their violent beauty. They challenge our understanding of fundamental physics, particularly regarding the behavior of matter under extreme conditions. Such events serve as a natural laboratory for testing theories of nuclear physics and gravitational behavior, pushing the boundaries of what we know about the universe and its latent mysteries. Thus, the collision of two neutron stars is not merely an event of destruction, but a profound journey into the heart of the cosmos, one that continues to enthrall and inspire our quest for knowledge.